Hello everyone, this is Jim Chastain with EasyPower. I'd like to welcome you to our Thursday webinar series. And we have a guest speaker today and a highly anticipated topic. Before I introduce our guest speaker, I would appreciate your attendance and involvement in our poll questions. So let's run a couple of poll questions for today germane to the topic. So first question is, how comfortable are you with the per unit representation of electrical system? Just get some feedback on people's association or comfortable level with this type of technology or shorthand. And as we end the year out, I wanted to thank everyone for supporting EasyPower and attending these webinars. So let's leave this open for about another 5 seconds. Looks like we have a quorum. All right. And here's how people weighed in on that response. So I think we have a good basis for discussion to start. And then secondly, what type of systems do you normally work on as far as your responsibilities? And again, we'll give this a few seconds to have everybody kind of chime in. We intentionally have some overlap here, thinking that we could simulate some questions about how that topic's going to pertain to one group or another. All right, looks like we have a quorum. Thank you for participating. Here's how people have kind of voted on this category. Excellent. Again, thank you once again for joining us today. Greg Harstine is a consulting professional engineer specializing in electrical distribution systems and electrical safety in the Canton, Ohio area for over 20 years. He's also an associate professor of practice, electronic engineering technology at the University of Akron College of Applied Sciences and Technology. We're very happy to have him as our guest speaker today. And with that, Greg, let me turn the presentation over to you.
Very good. Thank you, Jim. So I think everybody can see my screen now. Is that right, Jim?
Yes, it looks good.
Should be good. Okay. So first of all, I want to thank everybody for being here. It's a topic that I really enjoyed teaching and of course using in my practice. And hopefully I can expand your horizons a little bit today with the material I'm going to provide for you. I was also glad to see the responses to the poll questions that we had. I was a little bit concerned that maybe we'd get too much interest in the higher voltages. So being that most everybody is in that 34.5 kV and below range, makes me feel a lot more comfortable because that's where I spend most of my time, functioning more as like a plant engineer rather than in utility systems. So thought I'd just take a minute to talk a little bit about myself, see if I can get this working. So I've been a full-time professor for about 20 years, predominantly in power system analysis and design. I teach our NEC classes and have for several years. Also get into industrial controls and PLCs and have taught a lot in the field of electrical machines. Cornerstone Electrical Services is my business that I incorporated about 1999, and did a variety of things, and I felt like I got in on the kind of the front end of applying flash analysis to the field of electrical safety with one of the plants that I was doing some work at. So it's been fun for me to watch the 70E as it changes throughout the years. And one of my big tasks currently is allowing my approach to be flavored by the new fault calculation studies that were done. So that's going to take a little bit of time. So I evaluated several different packages when I was looking for something to do the analytical work for me in 2000. It was about 2003, and for me the bottom line was I wanted something that was Windows based, and at that time EasyPower was the only one, and I found that all the Windows and Microsoft, shortcut keys and all that kind of good stuff worked. That's kind of old hat now, but was to me it was pretty important at the time. And so I went with EasyPower. It turned out to be a really good selection, and have really enjoyed using the software over the years. I do a lot of safety plan implementation for mostly small organizations in the area, and function a little bit as electrical plant engineer for a couple facilities in the area, and then I also do some electrical distribution system design. So that's a little bit about me. And so I'm going to start us today just with basic short circuit ratings on this is typical low voltage equipment, just to kind of set a playing field for us. 10 kA equipment is the stuff that you typically find at local retailers, and then if you know a little bit about what you're doing and look a little bit harder, you can find the higher short circuit ratings equipment. My biggest problem with the folks that I work with is most of everybody in the field hardly ever pays attention to this, and so as I'm doing training, this is something that I try to emphasize and educate people about. I also think that as we talk about transformer impedance and fault calculations and things like that, I think it's also does a good job of sensitizing employees to, they really need to know where they're at on electrical distribution system. We could spend hours and hours looking at this in a variety of transformers and things like that, but I really just tried to keep it very focused because 45 minutes isn't a lot of time, and we'll get to some hopefully some good calculations that you'll find informative and quick and to the point. So I see a lot of Score D equipment with a 65 kA rating, but in this mix I oftentimes see breakers intermixed with panel boards of the incorrect rating. So I really try to bring it to folks' attention and get things corrected and pass along good information. So first thing I started with was just a couple of, you take a look across the board here, got two examples of transformers, two with a low voltage of 480 volts, two with a low voltage of 208, a 2000 and a 1000 kVA. And if we look here at the 2000 kVA with 5% impedance, I'm going to go over these calculations, but here's just the quick results. If we have a transformer that's got 2000 kVA that's got a percent impedance of 5%, that turns into 0.05 per unit. We take the rated current of that transformer divided by 0.05, we get 48,000 amps. So on a 2000 kVA transformer, that's the available symmetrical available short circuit fault current. These are really common. It's really common to find these quick calculators in like a spreadsheet form, and sometimes it's real nice to be able to just do a quick calculation. 5% is always kind of nice because if you take 1 over 0.05, it's a multiplier of 20. So 2400 times 48, or 20 times 2400 is 48,000. Also, we're starting out here connected to an infinite bus, which is basically a utility that can supply an infinite amount of current and with no voltage drop and has no impedance in the utility system. So just to compare here, 1000 kVA to 2000 kVA with the same per unit impedance or percent impedance can only supply 24,000, a maximum of 24,000 amps to a fault. One of the curious things that I have been really trying to educate folks to is lower voltage systems are not necessarily safer. You really have to be careful what kind of, and have a notion of what size transformer you're connected to. So as we go from a 480 distribution system to a 208 system, if it's supplied by 2000 kVA at the same impedance, that available fault current now goes up to 111,000 amps on a 2000 kVA transformer. And with 1000 kVA, again, it's cut in half down to 55,000 amps. But a lot of the work that I do I don't see any fault currents hardly ever close to this. But they do exist at times, but the most I've seen is about 50 or 60,000 amps in practice. Another nice thing when you get used to using per unit is when you have parallel transformers, you can, I know I can just kind of picture this in my mind, adding a parallel 2000 or a parallel 1000. And it's just like from AC circuits world, we just have two impedances that are in parallel. When you parallel impedances, they cut in half in terms of overall impedance. And so if we stuck with the 1000 kVA here, that available fault current then would double if you had truly parallel transformers, which I've only seen once in the work that I do. So when I'm teaching this stuff, I wanted to put this into your hands. This is my approach to the per unit process. The per unit stuff that I do, we don't do symmetrical components. We don't do unbalanced faults, and I'm happy to get through the basics of balanced faults. So this is the process that I teach folks. For any given system, you want to select an S-base. And what I'm going to do here in the next few moments is talk about the per unit process, how it's developed, and then also compare it to the EasyPower software, because I do like to kind of just to kind of keep my skills sharp, walk between the two and make sure that one kind of verifies the other. So for a given system, we select a base kVA. For the examples I'm going to show you, I'm going to start with 2000 kVA. Then we take our system and we divide it into voltage regions. Now, the ones I've shown you so far, we only got two voltage regions, but we're going to add a third here later on. Then what we do is we perform what I call a change of base or a delta base on impedances as it's needed. Now, this is the shorter version of a change of base formula. There would also be a multiplier if the voltages were different. The new as you change per unit impedance on a transformer from one base to the other, if the voltages vary slightly, it also changes the percent impedance by the square of the voltage change. So most of the time, I try to keep the systems pretty simple, and so we don't incorporate a voltage change as well. So this formula is a simplified version of it. And so that's what we'll stick with. Then what we do is go into the different regions and we calculate I base and Z base as needed. And as I go from an infinite bus configuration today for my utility system and then provide an example utility system, we'll use this Z base calculation one time today. Okay? So if we go back to our examples that I started with, on the left-hand side here is, again, our 480, a 2000 kVA and a 1000 kVA transformer with a 480 volt secondary, showing the simple representation for it here. On the right-hand side here is kind of my approach to the per unit system. So I go in and in the middle here, hopefully you can see it, I've selected an S base of 2000 kVA. When I break my systems into voltage regions, I have my students, when we're doing this on a classroom setting, I ask everybody to draw dotted lines through their transformers and then break it into regions. So here we've got voltage region 1 on the 12470 side, and then voltage region 2 on the 480 side. And in this example, we're going to put a fault then on the 480 volt side. Now, there's no change of base to be done in this system. And so what happens when we take our percent impedance and we put it into per unit, hopefully everybody's comfortable with that. The difference between percent and per unit is just a multiplier of 0.05. And I will apologize for some of my complex number notations here. I kind of flippantly put a J in and remove a J, or add a 90 degree and remove a 90 degree. So in terms of everything we're going to do today, except the last example, it just means provides for a phase shift, I suppose, of 90 degrees in my calculation. So if I make the series impedance here of my transformer, I put 1 per unit voltage into my transformer. In the real world, that would mean I've got 12470 3-phase being applied, And if you know much about the per unit system, it doesn't matter whether the transformers are delta or Y connected. We choose the line voltages when we're doing three-phase stuff on both sides, and I always go through the calculations and show that the percent impedance remains the same. It doesn't matter what the connections are. And so in the per unit system, or I call this per unit world sometimes, when we got 12,470 going into the unit, that's 1 per unit. And it looks a lot like a single phase representation of the three-phase system when we're all done. So we put a short circuit here on the end of it, and my calculations down here, the actual per unit fault current that's going to flow is my applied voltage divided by my resulting per unit impedance. So it's 1 angle 0 degrees divided by J, and I make all my inductive reactances positive J. I've also seen this where folks will, trying to think, they'll apply like a voltage at 90 degrees. And there's a couple different ways that you can do it. This is just my system, but inductive reactances are always positive J, and capacitive reactances are always minus J in my approach. So we take 1 angle 0 degrees and divide it by J.05, which turns out to be a multiplier of 20, and we end up with this minus J20. We take that. In addition, I have up in my regions here also calculated my base currents in the 1270, 470 region and the 2400 volt region, because what happens in my per unit system, this current, per unit current, is the same throughout. So if I want actual currents, I have to take my per unit current that I calculated and go back to the particular region and multiply it by the base current. So now I go back to my 480 volt region with my J20, multiply it by the base current of 2400 amps, which in this case, when we have a simple transformer, single transformer, it also matches the rated current of the transformer, which I really didn't explain back here, but that's where those numbers come from as well. So we don't have a very complex system, we just have a single transformer. So I end up with, on the 480 volt side, my 48,000 amps. What I'd like to do next then is add 1,000 kVA. Let's take a look, and let's take our 1,000 kVA transformer and put it into a per unit system where we use a base system, where we use the S base of 2,000 kVA. When you do that, we have to do this change of base calculation, where we take the original impedance of the transformer, which was J.05, and this is something that you might do if these transformers were going to even be connected radially, and you were going to do per unit calculations with them. If these guys were both tied to the same bus and we wanted to put them into the same per unit system, and we were going to establish S base as 2,000 kVA, we'd have to do the change of base on the percent impedance here. So we take the new, which to the 1,000 kVA transformer, the new base VA is 2,000 kVA divided by 1,000, which is a multiplier of 2, and we end up, so in this system then, if I had it in a system with a 2,000 kVA transformer, the impedance of that transformer would look twice as much as if it was just on the base, its own base, which is what's reported on the nameplate of the transformer. So now we do these calculations, but because I chose S base of 2,000 kVA, when I go calculate my base current in this region, I've got to use S base for my system. In the per unit world, my S base stays the same. It doesn't matter what voltage region I go to. You'll see as I add a second transformer here. So our per unit impedance now, or I'm sorry, our per unit current becomes 1 over J.1, which now goes to 10. We take our J10 multiplied by 2,400 amps, and we get 24,000 amps. And that's what we got before, our 24,000 amps. So there's just a per unit coverage of where those currents come from. And I also put down here the various ratings on equipment. So when folks are putting in, I get a lot of calls to put in a 200 amp or a 400 amp panel board. These are the types of things that you want to know. When I may want to discourage somebody from going to a local retailer and getting a cheap 200 amp panel board. and installing it for this very reason right here, as well as installing breakers in panel boards. You have to be careful of that as well. So these are the standard short circuit ratings that I'm familiar with. There may be a few more that I'm missing. I know that on fuses they go to 200 and 300 Ka as well. The other thing I didn't mention is we use a lot of square D equipment in this area, and so I know the QO line of square D breakers and equipment are 65 Ka. And then when you get into the I lines, I think you can get a couple more square D I line panel boards. They get a couple of more interrupting rating. So now going to EasyPower. Here's the one-line diagram for EasyPower for those 4 transformers. And to me, this is, when we look at utility 2 here, this is EasyPower's default representation for what I would call an infinite bus. And so that's the one-line diagram. And then here's the fault currents that are generated with those transformers, with those ratings and impedances. And you'll see here, I also put the currents at the bottom here that show the fault currents that we calculated using the per unit way of doing it. So very similar here. Now we'll see some differences here that in some of these examples that I don't necessarily have an explanation for, but we can chat about that. So okay. So with that in mind, serving as a basis here, the next thing I want to talk about is, well, as for different transformers, they may have different percent impedances. And so here's a couple of examples where I took the same transformers, and rather than having 5% impedance, they have both transformers have 7% impedance, which is kind of high in my experience. Sometimes I've run into stuff that was in this between 6 and 7%. One of the things I didn't mention is I worked for a local transformer repair shop for a number of years, and I bought and sold transformers for a long, long time. And these transformers were our bread and butter. Pad mounts in this size, unit substation types in this size, and so I feel like I have a fairly good idea of what common percent impedances are. That's why I'm real comfortable using 5% a lot of the times. So you can see here it's gone from 48,000 amps at 7% impedance down to 34.2 Ka on the 2,000 kVA at 480 volt. On the 1,000 kVA at 480 volt, it goes from 24,000 down to 17,000. On the okay. Now I stuck with the 480, but I looked at decreasing the percent impedance, and because I went up by 2% above 5% in this example, I went down by 2% in the 3%. So you can see what happens here. It goes from 48,000 to 75,000 and 24,000 up to 40,000. So that's the impact that the percent impedance can have on available fault current. And so those impedances are not all consistent. It's based on the manufacturer of the transformer. And transformer manufacturers, I know at the place where I worked, what we did is we short-circuited the secondary on our transformers and ran the voltage up until we had rated current flowing. And that voltage that we got to divided by the rated voltage is also the per unit impedance of the transformer. So when you get in small pad mounts and pull mounts, they don't test every transformer, but that is where that number comes from. Again, listing of equipment ratings. So here we're going to add I thought I'd start by adding a 500 kVA transformer in series with a 2,000 kVA. So I went back to my 2,000 kVA, 12470 to 480 with a 5% impedance, and also have the EasyPower system over here on the left. And so here's the same transformer that we had. But now, and I do this a lot, I'm sure many of you do it as well, when we have 480, what we don't have in a 480 system is 120 volt for receptacles and low voltage power, and sometimes lighting as well. So it's real common to have another transformer here. So I just started this process by taking a 500 kVA transformer, and that is 480 to 208, and we can, on a 500 kVA transformer, that's a lot of current. So we could add, it would actually take a very large panel board on this side to take advantage of the full load rating of the transformer here. But this is just an example. So as we take that transformer and put it into our per unit system, again, my base VA is 2000 kVA. I divided it now into 3 voltage regions, 12, 470, 480, and 208. I have my 3 base currents calculated here, 93, 2400, and 5552. And again, here's my change of base calculation. And so I take my 5% on my 500 kVA transformer. To put it into my per unit system, I have to do a change of base on it from 2000, or from 500 kVA to 2000. So that becomes a multiplier of 4. And so now that transformer looks like a J.2 per unit impedance. And that was a big part of the motivation for me doing this webinar is I do a lot of training of plant floor electricians. And what I've discovered is, as I said, it really is highly dependent. The available flash where you're working is highly dependent upon the size of the transformer that is feeding your system. And so I think this gives a good representation of how the fault current changes as you go from where you may get, in this case, you know, the examples we're showing here, the assumption is we're buying our electricity here at 12,470. And so the further you get away voltage-wise from the incoming service and get into these smaller transformers, your available fault current goes down. And we're not even looking at fuse interrupting characteristics and things like that. Just trying to give a good feel for how the fault current changes as we get to these smaller and smaller transformers. And it's because the impedance of this transformer goes way up in comparison to my 2000 kVA. So now in the per unit system, this is just a simple series circuit. My 2 impedances add together. So in my 208 volt region here, my fault current is 1 over J.25. That's the sum of these two, which gives me, multiply that out, we get minus J4. Multiply that by the base current in the 208 volt system, and my available fault current now is 22,208 amps. Okay. The same fault in the 480 volt region now amounts to 4,800 amps. That would be in the 480 volt system. And I'm really only looking at the low voltage systems. Okay. Now, when we do that in EasyPower, we get the same thing: 2,000 kVA, 12,470 to 485% Z, and a 500 kVA. And on the fault current, we get 22,212 with that guy. The other thing I wanted to do is, which I thought was a good example, it's real common to get a call from somebody when they need to add a low voltage or a, you know, less than 250 volts, 240 volt, 208 volt, 200 amp panel. And a typical design like that tells me that we're probably going to need to set a 75 kVA transformer. So now, and that's kind of what, you know, 200 amp, 225 amp distribution panels are very common. And so that's kind of a scenario that we might be looking at. So we set this 75 kVA transformer into this system, and here's what happens. If we notice that 500 kVA looked like a J.02 in per unit world, well, what happens with that 75 is now it goes above 1 even. So we take 2,000 divided by 75 times the 5% impedance of that transformer, and that per unit impedance becomes 1.33. We plug that in here, And again, simple series circuit with a 1 per unit voltage applied to it. The impedance, per unit impedance of the system is J1.38. That gives us the per unit fault current of 0.96, which may sound a little bit funny, but you got to remember we're down here in the 208 volt region on the low voltage side of a 75 kVA transformer. But so our fault current is going to be higher than 200 amps. By the way, the rated current on this transformer I think turns out to be 208 amps. Okay, but when we multiply that 0.96 by the base current that is established from the base VA of 5252, we get a fault current of 5,329 amps. And so that's on the 208 system. On the 480 system, the same per unit current times the 2,400 amps of the base current in that voltage region gives us 2,304 amps. And again, this is what really catches my attention. When I add smaller and smaller transformers, the impedance of those transformers looks really high to the system. And that's just, it's kind of one of the tools that I carry in my bag as I go about my business doing safety work and working with people to implement safety plans. I also took the same thing here and put it into EasyPower. Now here was a number, and I worked with this trying to explain why, but this is quite a bit smaller. I only got 4,000 amps compared to my 5329 here. Anyway, still less than 5,000 amps. So that's the 75 kVA. Hopefully that gives you some insight into how smaller transformers impact available fault current in electrical distribution systems. The other area that I try to emphasize too is when we get into control transformers, and again, when you get into a control cabinet, you don't know whether you're going to be supplied by a DC supply or a transformer, a control transformer, or you can have control voltage, believe it or not, on a 208Y120 system, we can have control voltage coming off of one of the phases of our supply transformer, whether it was a 75 kVA, or if we go back up above to one of our, like a 1,000 kVA 208Y. That's why I think it's so important to try to, one of the most important things I try to do, which I think is hard for plant floor electricians to comprehend, is just understanding one-line diagrams and knowing where your control voltage comes from. It can be a good thing, but it can be bad. You just got to be careful. If you're coming off a really small, control power transformers get down less than 1 kVA, 500 VA and 250 VA. So they're an enormous looking impedance for the rest of the system in that case. So extremely important to know where your supply voltage on a system voltage that you're working on is fed from.
Greg, excuse me, this is Jim.
Yeah.
I have a couple
Yes,
people.
Jim.
A couple people asking why at the bottom of your slide you're showing in the 480 volt region for the lower transformer. You show 208 and then 480 at the bottom.
Where's that?
You have three regions of your per unit system, and
Yeah.
on the right hand side you show your current on the base as 552, and at the bottom when you go to utilize the number, we're still calculating the 480 volt region fault current.
You mean down here in the
Yes.
480 where it says well, this is the fault current in the 480 volt region.
So that's going to be in the
So
480. Okay.
In region 2. Does that make sense?
I think it does.
This 5329 results in a fault current in the 480 volt region of 2304.
Okay.
That's what that means.
Yeah, I think that's what I misunderstood. All right.
Mm-hmm.
Thank you.
Yeah, you're welcome. More questions?
No. Let's see. Yeah, there is one more. The Very interesting presentation, how to reduce short circuit current with small transformers. Is it economically better option than using higher capacity low voltage breakers? I'm not sure if I understand that one. It's a European question.
Yeah, would you read that again?
So this is coming from our friends in Croatia. It says, it's how to reduce the short circuit current with smaller transformers. Is it economically better than using higher capacity low voltage breakers? I think that the suggestion was the reason we're doing this is to use lower capacity breakers in the low
Yeah,
voltage.
and that's not necessarily the case. This really, my motivation for this is to understand how smaller transformers impact available fault current.
Right.
That is certainly an option that, yes, you can use if you break a system up. I mean, you have the expense of more transformers if you want to completely utilize your system capacity. And I have not done an economic analysis of what we're discussing here. It also, I mean, from a safety standpoint, it makes a lot of sense to incorporate these, transformers to reduce the available fault current. But the flip side of it is it does add impedance to the system, which contributes to voltage drop in the system. So it's trade-offs that you have to look at.
Okay, go ahead.
Good. Okay, so the last thing that I have on the agenda to talk about is, well, what happens when we add a system, when we have a utility system that's not ideal, it's not an infinite bus. And so here's an example actually from a job that I just did this last year. In our area, we are served by First Energy and American Electric Power. They have a lot of 12470 distribution voltage. And so I contacted the local power company at one of my facilities. I was doing some work, and this is the three-phase characteristics that they gave me. The serving voltage was 12470. Their available short circuit capacity was 2383 amps, and the X over R ratio is 3.55. Now, what we need to do is we need to turn this information, this is what I do anyway. Now with EasyPower, it's real nice. You just plug these numbers into the system. But if you want to know what these things are, how these things work in the per unit world, we need to convert this. First of all, we need to convert it to an ohmic impedance. And because we have an X over R, it means we're going to have some J and we're going to have some R, or JX. And JX is going to be a lot bigger, 3.55 times bigger than R. And so we need to convert these items into ohms and then take those ohms and put them into the per unit system. Now, how's that done? Well, the information, the short circuit current here that is relayed, you have to think of your system as basically a single phase representation. And so we take the phase voltage, if the line voltage is 12470, we divide that by square root of 3, that gives us 7200. That would be the line to neutral voltage then. And the available fault current, phase to ground then, or phase to neutral, 23 is the available fault current. So it's voltage divided by current that gives us impedance. So this gives us the magnitude of Z that has X and R, okay? This is the magnitude of Z. Well, now once we have Z, impedance is effectively a right triangle when we have R and X in it. So the next thing we can do is go calculate what theta is of our impedance triangle. That comes from the X over R ratio. It's simply the inverse tangent of the X over R that you're given. In this case, it turns out to be 74.3 degrees. And then again, thinking in terms of a right triangle, the resistance in ohms is the magnitude of the impedance Z times the cosine of theta. That gives us 0.08817. I did these kind of quickly. Sometimes I get sines and cosines backwards, so hopefully I didn't do that here. And then JX is the sine of the angle times the impedance, and that gives us 2.91. So the system then, in terms of ohms, looks like a series impedance of 0.817 ohms resistance and a 2.91 inductive reactance. Then we have to take, I call that the actual impedance, we have to convert that to per unit. And way back before, up above here in my presentation, Z base is Z base squared. So I showed it as 12470 times 12470, Z base squared over 2000 kVA. And that's a three-phase calculation. You could do that with a single-phase calculation. You get the same answer, just I think there's a square root of 3 in there somewhere. But this is my base impedance right here. So take my actual impedance divided by the base, and that gives me the per unit impedance. And then I think the last slide I have is I took the system that we just had, that was the 75 kVA transformer and the 2000 kVA transformer, and I added my system impedance back here. And when we compare those, again, the big contributor here is that 75 kVA transformer. In fact, if you know, the old engineering tricks that we play, we ignore things that don't have much impact on it. We could almost ignore the rest of this series impedance, including the utility impedance, and just look at that transformer, and we wouldn't be far off. But the bottom line is, when we add those four impedances up, we get 0.011 plus J 1.75. Divide that into a voltage of 1 per unit that's applied, and we get a 0.587. Now, because we have some resistance and reactance, we're going to get a slight angle. But if you notice, we're only at 89.6 degrees. We're not far from 90 degrees, which is would indicate completely reactive. Multiply that in the 208 volt region times 5552, and we now get 3172. And before we had gotten 5329. So in this case, it had a fair impact on the available fault current. That's why another illustration, I think, of the importance of getting system information, because it can reduce the fault current. The thing we have to be careful with, when fault currents are being reduced in some fashion, that's also increasing the trip time on breakers and fuses. And so sometimes it can have a positive impact on available flash, sometimes it can have a negative impact on available flash. So I added this. Oh, this is the showing the EasyPower plug-in this system here in the utility in EasyPower. I plugged in the actual utility system and my 2000 kVA, my 75 kVA transformer, and you can see we get 3915 amps there doing it that way. And I think that's the end of my presentation. Yep. So I would be happy to take, we're getting close to our 45 minutes here. I'd be happy to take any questions that we have.
I think we had 3 earlier, and I think what you just went through answered most of those. This is a interesting take on the arc flash paradox that I kind of emphasize for the people that think it's okay to just put your protective device on the primary side of the system.
Oh, yeah.
Well, thank you, Greg, for a good presentation. If any other questions come in, we can answer them via email. And we thank everyone for attending today.
Yes, thank you very much, everyone. Thank you, Jim.
Have a good day. Happy holidays.
Thank you. You too. Everybody out there too.